Hello everyone, welcome to MEC 1321 Engineering Statics. My name is Dr. Stewart. Today we're going to go over some additional examples that we were unable to cover in class. Thankfully we were able to go over most of the material in class, so this should just be 3 quick questions for us to solve. So let's go ahead and get right to it. The first example is example 216. In this problem, we have a hook, and it has a force with a magnitude of 100 newtons coming out of it at a set angle. And there's 2 axes of interest, which are axes U and V. And this problem asks us to find the magnitude of the force that is projected on the U and the V axes. And note that the problem asks you to find the projected force and not the components of force along these axes. With the emphasis on projected, let's go ahead and try to solve this problem. The first thing we do is we list our knowns and unknowns. We're given some of the angular information of the force vector relative to the U and the V axes. We're given the magnitude of that force vector, which is 100 newtons, and we're asked to find the magnitude of the force vector projected on the U and projected on the V. So in order to do this problem, when it states projected, we can simply solve it using a cosine relationship. If we look at the diagram, we see that it's indicated that we can create a right triangle from the force vector F to the axes of interest, and the force that's directed along the U axis is called the projected force. When we do that, we can simply apply trig. And we'll find that apply trig or apply the dot product rule, and we'll find that the force projection U directed along the U axis is equal to the magnitude of the force times cosine of 45 degrees, which is 70.7 newtons. We can also do the same thing for the projection on the V axis, where the force magnitude in the force projection on the V axis is equal to the force magnitude times cosine of 15 degrees, which is equal to 96.6 newtons. And so it's very clear to see that if we're projecting the force, we can directly use the cosine law. Now, it's important to note that these magnitudes that we found, these projected magnitudes, are not equal to the magnitudes of the components of the force vector that's directed along U and V. And what I mean by this is that the projections that we have are not equal to a way for us to take. We're not using the triangle rule and finding the subcomponents to find the final vector. What we're doing is we're finding just the projection of the force vector along a particular axis. And the values of the components and the projections are not going to be equal. So the components can be found by simply using the parallelogram law and then subsequently the triangle rule and applying the law of sines. So it's very important for you to be able to distinguish between what is a projected force and what is a component of force. Now generally you're going to be asked for the components of force, and you're going to need to use the parallelogram and the triangle rule and subsequently the law of sines. But in the case of this problem, it asks for the projection. So just try to be mindful when you're given problems on what approach is necessary given that type of problem. Now let's go ahead and do another example, which is example 217 from the book. This example is a little bit more complicated. We have a 3D structure here with established X, Y, and Z coordinate system. And it's an interesting triangular bracket type structure with a lot of dimensional information given. And let me try to clear this up a little bit so we can actually see what's going on here. So, we have an interesting bracket assembly here. We have a point A and a point B. We're given dimensional information for it. And we have a Cartesian force vector of 300 J newtons coming out of point B. And this question asks us to determine the Cartesian vector and magnitude of the components of the force vector that are parallel and perpendicular to member AB, right? So we have a force vector at point B, and we need to find the components of this force vector that are parallel and perpendicular to member AB. So that the force vector that is projected along AB and the one that is perpendicular to AB. Now remember that, notice that this problem asks for the components. So we do need to have a consistency between those subcomponents using the Pythagorean theorem will equal the same magnitude of the Cartesian. So let's go ahead and start this problem with our knowns and unknowns. We're given positional information for point A and point B. We're given the Cartesian vector for our Cartesian force vector. And what we need to solve for is the magnitude of the parallel component. So force AB, the component that's parallel to line AB is going to be called force AB. And we need to find the magnitude of the transpose, which is the perpendicular component from line AB. And then also we want to find them in the Cartesian vector form, because that's what the problem asks us to do. So let's go ahead. Well, let me go ahead and add back this information here. So let's go ahead and construct our free body diagram. We establish our coordinate system, and we establish, the positive directions for the coordinate system. We put in our points of interest, and then we draw our knowns as well as our unknowns, where our knowns is the force vector F, and our unknowns are the force vector directed along AB and the force vector that is transposed to AB. We also know that there's some kind of unit direction from point A to point B that we need to find in order to actually construct these the AB and the AB transpose terms. So now that we've created this free body diagram, we've put in the information that we have. Let's go ahead and think back to the theory on what equation could we use in order to solve this problem. Now we know that a very useful property of the dot product is our ability to find parallel and perpendicular components, and also to find the angle in between two vectors. We're going to use, in this case, the usefulness or the property of finding parallel and perpendicular components. In order to do that, we can use the following equation to find the magnitude of the parallel component to the unit direction AB, where the magnitude of FAB is equal to the magnitude F times cosine of theta, which is also equal to the force vector Cartesian dot product unit direction vector AB Cartesian, right? So we know the force vector portion, but we do not know the unit direction vector directed from A to B. So let's go ahead and find that unit direction vector. We know that the unit direction vector is going to be equal to the Cartesian position vector divided by the magnitude. So let's go ahead and find that Cartesian unit vector. For this problem, it's very simple. A is at point 0. So when we want to find RA to B, we very simply just need to put in the values of the position for B. And so we can go back up to our diagram, look at the positional information for B. We find that on the x-axis it's positive 2, on the y-axis it's positive 6, and the z-axis is positive 3. So we'll find that our position vector from A to B is equal to 2i plus 6j plus 3k meters. Now that we have the components of this position vector, let's go ahead and find the magnitude or the length from point A to point B. We can use Pythagorean's theorem. We put in our components, we square the components, and then find the square root, and we'll be able to find the magnitude of RAB. And then very simply, we take the Cartesian vector and the magnitude, and we can calculate our unit direction vector. So now that we've done that, we've found the unknown, we can now calculate the magnitude of the force that's directed along AB, where the magnitude of force AB is equal to the Cartesian vector F dot product UAB. So then, with that known, we can go ahead and do the multiplication, where we take the terms. We'll do the dot product multiplication where we separate the terms out and multiply each by each other. We know that when we do the dot product, that terms that are not coincident, so terms that are not like, will become 0. So we find that I dot j is going to be 0, j dot k is going to be 0, and the only term that will remain will be 300 times 6 over 7, which results in our magnitude, our force AB magnitude. Now it's important for you to go back and revisit theory on why the I dot j term and the j dot k term are eliminated. And it's very simply the application of the dot product rule where the unit directions become the vectors. So now that we've done that, we'll find that the magnitude FAB is equal to 257.1 newtons. So now that we found that magnitude, we do know that we have the magnitude along AB. Let's go ahead and find the Cartesian form. And very simply, the Cartesian vector of the force directed along AB is going to be the magnitude of that force times the unit direction vector from A to B. And we've already found that unit direction vector. Thus, the Cartesian force vector AB is going to be equal to 73.5 I plus 220 J plus 110 K newtons. So now that we've done that, we need to find the transposed component. Now, since we're finding the component directed along AB and transposed to it, and it is the component, it's clear that if we were to add the subcomponents, meaning the component directed along AB and the one that's transposed, that they should sum and equal to the initial Cartesian force vector. So we simply apply that equation where the force vector is equal to force AB plus force AB transpose. Well, if we rearrange this problem, then we find that the Cartesian force vector that is transposed is equal to the Cartesian force vector minus the Cartesian force vector directed along direction from A to B. And when we do that, we see that we have the two Cartesian vectors on the right-hand side, and we simply apply them, do the addition, subtraction, and we find that our force vector that is transposed to direction from A to B is equal to negative 73.5 I plus 80 J minus 110 K newtons. Another method that we can use in order to find the force that is transposed is to use Pythagorean's theorem, where with Pythagorean's theorem we find that the magnitude of F should be equal to the square root of FAB squared plus FAB transpose squared. So we can simply rearrange this equation, and by rearranging it we'll find the magnitude of the force AB that is transposed. And then simply verification is to take our Cartesian vector that we found, take the magnitude that we found, and verify that they're identical to each other. Verify that the left-hand side and the right-hand side of the Pythagorean theorem equation is valid. And that's a fairly simple way for us to solve these problems. Again, it's important to note when we're asked to find components that the sum of those components is going to be equal to the resultant vector. But when we're asked to find the projection, that the sum of the projections is not going to be equal to the resultant vector. In general, don't worry too much about projections. We're primarily going to focus on dealing with problems of components. But if you do see the word projection, just be mindful. So let's go ahead and do this last example here, which is example 218 from the book. In this example, we're given an interesting type beam structure, and that has a position A in it, and it has a position B in it, where we're given dimensional information. And at point B, we have a force vector that is directed at a certain angle relative to the line AB that has a magnitude of 80 pounds. And that angle, we call that angle theta. And this problem, it asks us to, well, also we have a point C, which we're given dimensional information for. In this problem, we're asked to find the angle and the magnitude of the force component on line BA. So the magnitude of the force the force component that is directed from B to A, given this particular problem. So let's go ahead and do the first step, which is identifying our knowns and unknowns. We're given the magnitude of the force, which is 80 pounds. We're given position information for point A, B, and C, and we're asked to find the Cartesian vector or the component, the Cartesian vector component that is directed from B to A of the force vector that we're given. And we're also asked to find the angle that is in between the force vector and the axes of interest. So let's go ahead and draw a free body diagram. In the case of this free body diagram, I simplify it greatly. I completely remove the body, free it from the body, and focus just on the points of interest. So we create our coordinate system, and we describe a positive x, positive y, positive z, right-hand rule coordinate system. We put our points of interest, point A, B, and C. We draw the given force, which is F, which has a magnitude of 80 pounds. And then we draw the unknown, which is the Cartesian force vector directed from B towards A, as well as the angle that is in between F and FAB. Now that we've done that, let's go ahead and take the position vectors that we have, and let's take the points of interest we have and create position vectors for them relative to the origin, which is point O. When we do that, we find that A is equal to j feet, which is 1 j feet. B is equal to 2I plus 3j minus k feet, and C is equal to 2I. So now that we've done that, let's kind of think a little bit further. We know that we need to find the unit direction vectors from point B to point A, so we know the direction of line from BA. And we also need to find the unit direction vector from B to C, which is the direction of our force vector. So let's go ahead and find the position vectors first. And so we can do that simply. RBA is going to be equal to position vector A minus position vector B. And then RBC is going to be equal to position vector C minus position vector B. And we collect the like terms, the ij and k components, and we will find the values of those position vectors in Cartesian form. Then we can simply apply Pythagorean's theorem, and we can find the lengths or the magnitudes of the position vector. Let's restructure. Let's rewrite that to position vector BA and position vector BC. We find the magnitudes of them. So now that we've done that, we can very simply use the dot product rule in order to help us find the angle, where the dot product rule describes is a way to describe the angle between two vectors. Well, in this case, without even using or constructing our unit direction vectors, we can directly use our position vectors to find the angle. The dot product is vector based, so if you have a position vector or a unit direction vector or a force vector, as long as you have that information, it will find the angle between them. So in this case, we use the position vectors that we found, and we apply them in the dot product rule, and we know that we found the Cartesian vector form as well as the magnitude of these vectors, so the only unknown becomes theta. And we very simply rearrange this equation, solving for theta, and we'll find that theta is equal to 42.5 degrees. Now that we found that angle theta, let's go ahead and find the second part of this problem, which is the Cartesian vector of the force that's projected from point B to point A. So remember, if we're given, remember that the magnitude of a force vector on a specified axis is equal to the Cartesian vector of the force vector dot product, the unit direction vector of the specified axes. So if we apply this theory, which is in the previous video, we'll find that the magnitude of our force directed from B to A is going to be equal to the force, the parent force, which is that force vector, dot product, the unit direction vector from B to A. Well, we can construct our unit direction vector from B to A very simply as the position vector Cartesian divided by the position vector's magnitude. and we put that information in. Now that we have our unit direction vector, let's go ahead and find it. Let's find let's go ahead and find our force vector, where our force vector is equal to the magnitude times the unit direction vector BC, and that force vector is that Cartesian force vector is going to be 80 pounds times negative 3j plus k divided by the square root of 10, and we get the Cartesian vector form. And from that, let's finally find our force vector, our force magnitude, which is directed from B to A, which is going to be equal to the force vector dot product to unit vector BA, which will give us a value of 59 pounds. I'm skipping a number of steps here, but it's very important for you to understand the theory, be able to apply that theory in order to solve your problems. So that pretty much covers the additional examples that we didn't get to cover in class. If you guys have any questions, please put a comment on the YouTube. I'll try to get to your questions. Definitely start doing your homework now. The homework for this section is going to be due very soon, so it's important for you to kind of chop up the homework, do a couple problems each day. It'll really make it a lot easier when homework is due. Please do try to do additional examples and exercises. And if you don't understand some of the steps, sometimes the steps are only, you can only find those steps by actually exercising them and trying them out. So please do try to do some examples. It's really one of the best ways to learn. Thanks for your time and attention. I'm Dr. Stewart, and I'll see you guys again.